Hey, this is a video that talks about for the mathematical problem solving, your exam, the second exam. And so I've worked through a number of these problems already, and so I have the work here, and I'm going to just go over the different ways that you could work the problems just like we did in class, and this will be a good study guide, at least I hope it will be. So I'm going to take this off, kind of move it over to the side, and then I'll bring this up. And what we have is the first problem where we have our carnival bears. Now the carnival bears are, you got three of one type of bear on the left and three of another bear on the right. You have 7 pedestals, and you got to slide, you got to jump, and one set of bears can only go left to right, the other bears can go right to left. And what you need to do is you need to find out how to get the bears to swap places. And we did that in class. You did pennies, quarters, this, that, and the other. You did it by acting it out in chairs, humans in chairs. And you come up with a rule that you all come up with that's x squared plus 2x. Now, what I need you to do is on the test, you need to not just know that rule, but you got to be able to explain and be able to get there. And I need to realize how you got there. So, realizing how you got there means that you can create a table of sorts. So, when you do an example, when you had 3 bears of one of each color, it took 9 jumps. When you had 4 bears of each color, it took 16. When you had 2 bears of each color, it took 4. And you look at that pattern, you realize, wait, I take bears times bears, and it gives me the number of jumps. So that's bears squared. Well, for the slides, you see a pattern that 3 and 6, 4 goes to 8, 5 goes to 10, and so in order for 3 to get to 6 the same way that 4 gets to 8, I need to add the bears to the bears. So the number of bears times 2 gives me the number of slides. So the rule for jumps is b squared, slides is 2b, and total will be the adding of them together. However you need to explain that to me and put it into a reasonable response, then that's how we'll get it graded. Next, we did our crossing the river problem. Now, the crossing the river problem said simply this: you got 8 adults, you got 2 kids, and you need to cross a river. You can have the boat, 1 adult in the boat, 1 kid in the boat, or 2 kids in the boat. After you do that, everybody can row the boat, and you need to find out how many total moves it takes to get them across the river. So you can draw pictures and this, that, and the other and get them across. Then you realize that 8 adults, it takes 33 trips. Well, then you got to come up with a rule. I got to ask you a rule that if adults changes and the kids stay the same, how do we find a rule that says no matter how many adults we have, we can predict or know how many actual trips it takes to get them across the river? So you're going to need to illustrate to me how you work a simpler problem or a more advanced problem in order to get the rule, to find that pattern. Well, 3, if I did it with 3 adults, I did it and it took 13 trips. When there were 2 adults, it took 9 trips. And you look between 8 and 33, 3 and 13, and you're really not seeing a pattern there. So we be a little more organized with it. When I have 1 adult, it takes 5. When I have 2 adults, it takes 9. When I have 3 adults, it takes 13. Then we see a much better pattern showing up, to where there's a difference between 5 and 9 and a difference between 9 and 3 that's the same. You would add 4 each time to get to the next one. Well, we talked about in class how that 4 becomes the coefficient of your variable, the number of adults. So you can say 4 times a, and if I say 1 times 4, I get 4. I got to get to 5, so I got to add 1 more. And 2 times 4 gives me 8. I need to add 1 more to get 9. And 3 times 4 gives me 12. Add 1 more, get 13. So that's my rule. And somebody else in class talked about a different rule where you multiply the numbers together. So number of adults times 2 children, and then you multiply that times 2, and then you add 1. It still gets you to the same rule. Other way, you can say, well, when I draw a picture out, I get 1 trip, so 2 kids go across, 1 kid comes back, 1 adult goes across, and then the other kid comes back. And that took 4 trips to get 1 adult across. But the 2 kids are sitting right over here. You got to get them back. So you got 4 for every adult, and then that 1 last trip to get the 2 kids back across the river. That's how you would kind of need to explain it to prove that you can do it. Next, we do a problem where we went into the dollar signs. And so with the dollar signs, you have this. You have a dollar sign. Let me see if I can move this around so you can see it a little bit better. No, it's all together. So apologize, I'm writing over something here. But you have your dollar sign, and when you put one vertical line through it, it cuts it up into 4 pieces. Your other dollar sign, when you draw 2 lines through it, it cuts it into 7 pieces. When you have the dollar sign or the S cut by 3 vertical lines, you get 10 sections. When you do it in order, 1 line, 2 lines, 3 lines, you can see a pattern that we're adding 3 each time. So that 3 becomes the coefficient of our variable L lines, and then we'll need to add 1 more to get to the actual number of parts. You can see that algebraically through creating a table, and that's a sufficient way to prove that you can do the problem. Another way is you can look at it geometrically. Take this S for instance, when it's cut by 3 lines. Well, we have a top part of the S, we got a middle part of the S, and we have a bottom part of the S. Well, the top part of the S is going to be cut into 3 sections because, the top, the bottom, and the middle and the bottom, there's 3 parts, so each line crosses through 3 parts. Therefore, you take the line times 3. And then, when that happens, you'll notice that we're left with 1 on the end. So we have this line broken down into 1, 2, 3 parts, 1, 2, 3 parts, 1, 2, 3 parts, and we have 1 left over. So you look at it geometrically, the number of, we have top, bottom, and middle, top, middle, and bottom, and each line cuts it 3 times, and then we'll have that 1 left over at the end. Now, the way that we extended this problem is we had an additional set of problems addressing the cents symbol. Well, going back geometrically, what we just talked about, the cents now have a top and a bottom, so each line crosses 2. So you multiply times 2 times the line, and then you're going to have that 1 left over at the bottom. And so that's the 2L plus 1. You can explain it geometrically, or you can do it algebraically. Algebraically is, of course, going to be coming over here and showing the table. The table is that if I have 1 line, it breaks it into 3 parts. 2 lines, it breaks it into 5 parts. And 3 lines, it breaks it into 7. And the recursive rule here is you're adding 2 each time. Because you're adding 2 each time, you're going to be coming over here and multiplying by 2 times your line. And that's the recursive into the explicit rule for a linear relationship like this. And the S was drawn up here to just illustrate that we have 3 sides. So we're going to cut each line by 3, so times 3. And if we had more than that, 1, 2, 3, 4, we have 1, 2, 3, 4, 5, so we would multiply that one times 5. Each line would cross through 5 parts of that symbol. And the final explanation, or the final extension to this is I give you problems where, well, if we had 6 lines, how many? 10 lines, how many? 75, how many? And so those are extensions to this problem. Alright, good luck with that. And then we move over here to our problem where we had our money situation, where somebody is paid 10 cents, sorry about this, everybody is paid 10 cents on the first day, and then you double it the second day, and you double it the third day, and so day 1 you get 10 cents, day 2 you get 20, day 3 you get 40 cents, day 4 you get 80 cents, and then you start thinking, why am I working here? Well, if you extend it all the way out to day 21, you realize that you're going to get 10,400,000 and some odd thousand cents at the end of 21 working days, and you think, hey, that's a pretty good deal, I'll take it. Now, that's one way that you can work this problem. Given 21 working days, then you go in and you draw a table out all the way to the 21st day. That's fine, you got to Dallas. Another way is you show it with a pattern or algebraically. And looking here, we have day 1, we only have 10 cents. Day 2, we multiplied times 2. Day 3, we multiplied all that times 2. Day 4, we multiplied all that times 2. So what happens is, for whatever day it is, you're going to have 2 raised to that day minus 1. So for instance, day 4, we take our 2 raised to the 3rd power and then multiply it times 10. If we're on day 21, we raise our 2 to the 20th power times 10. If we're on day 1000, we raise our 2 to the 999th power times 10. And so that's an explicit rule dealing with exponents that could help explain the rule as well. Either way, you're going to have to do some long computations because you don't get a calculator on this, but you can either raise some 2's to some powers or you can create a table. But either way, you're going to have to illustrate how it is you're going to get to find out how much the person gets paid after or on the 21st day. So moving right along to the last part of this that gets you ready for the test is same concept of that type of problem, but now we have with 5 cents. And so I'll jump right to it exponentially, we're doing 3 times as much on this problem. So exponentially, you got 5 on the first day, times 3 the second day, times 3 the third day, times 3 the fourth day. So I'm going to have 3 raised to the day minus 1 power. So on the 10th day, we're going to have 3 raised to the 9th power times 5, which was your original cents. If we're doing it with the 4th day, then we're going to have 3 raised to the 3rd power times 5. If we're doing it on the 2nd day, we're going to have 3 raised to the 1st power times 5, or just 3 times 5. Or you can also just create a table and work it all the way out. Now I could give you just basic sequences here that would allow you or ask you to just complete the rule, and that would be 2 times 3 gives you 6, times 3 gives you 18, times 3 gives you 54. So the rule is times 3 times 3 times 3. Now 3 times 5 gives you 15, times 5 gives you 75, so my rule there is times 5 times 5 times 5. Here we notice that our numerator is times 2 and our denominator is times 3. Well, in order to do that, that means we're multiplying by a fraction, and we're multiplying by the fraction 2/3. So we say 2/3 times our answer gives us the next, 2/3 times that gives us the next, and 2/3 times that gives us the last. And then 5,000 down to 500, down to 50, down to 5. One pattern is you're losing zeros, but then after the decimal you're going to gain zeros. So the idea is really we're dividing by 10. You divide by 10 to get the next, divide by 10 to get the next, and divide by 10 to get the next. So that's all the sample problems that we did in class from the textbook and Section 3 or Section C. You need to still know about Section A and Section B and the problems associated with those. You need to work some additional problems from Section C that we did not do in here, and then be able to do the problems we did at the, with the other teachers. So good luck studying, and I'll see you when you come take your test.